Good evening, everyone. Welcome to the presentation. So this is our second part in the Introduction to Common Compilers Tools series. And this is going to be about technologies enabled by LLVM. So before going into the talk, we'll just introduce ourselves for people who are new here. So we are LLVM Social Bangalore. The meetup was actually started by Aditya and Reship Sharma in 2019 with the aim of building a strong compiler community in India. We organize meetups almost every month, and we currently have around 1,300 plus members on Meetup. And we welcome people who are experienced professionals, academicians, students, anyone who's interested in compilers and want to know about it and get started and contribute. And if you missed last week's talk, we talked about compiler engineer career. What does a compiler engineer do? How you can get started, and how you can reach out for mentoring, etc. And if you missed the talk is on YouTube, so you can check it out. Yeah, so let's get started. So what's LLVM? So LLVM is a collection of modular, reusable compiler toolchains and technologies. It's in a simpler word, it's a library to build compilers. And we'll talk in more depth about what LLVM is, you can see that LLVM is not just a single project. It has a lot of sub-projects, especially client compiler, Optas, which is the LLVM IR optimizer, and LLDB, which is the debugger, and a whole lot of other tools that's currently under the LLVM umbrella. So I'd like to welcome Prerana to talk more about it. Yeah.
Thanks, Pradeep. So the name of this session, the title of this session is technologies that are enabled by LLVM or technologies that leverage LLVM. So I'll just brief about the intent of this session. Basically, we want you to develop an understanding of the LLVM project so that we cannot go on covering whatever technologies are using LLVM, because that will be like multiple sessions. But whatever examples we will cover, we hope that you get an understanding that why they are able to use LLVM. And the next time you come across any project which is using LLVM, you will be able to understand how is it using LLVM. So the main reason why LLVM was created, it was created by Chris Latner and his team. So the reason was that they wanted to develop a modular and reusable compiler and toolchain technologies. Maybe we can go to the next slide and look at more detail. Yes. So this is my brief understanding of how we can interpret modularity and reusability. So let's say you want to develop, you have designed your own programming language and you want to write a compiler for it. So you can actually use the LLVM tool chain to do that. Just that you'll have to write a parser or basically the front end for your programming language, and you can then lower it into some LLVM IR, which we'll cover in the next slides. And you already have the infrastructure to convert it into machine understandable code already in place. So LLVM gives you that facility to convert it into a machine level language if you have just written the front end or the parser. And modularity is that, let's say you have everything in place, you just want to use a specific tool from it. Let's say you have some intermediate representation and you want to optimize it. So you will use a tool chain called OPT. So what I mean is that the LLVM infrastructure project gives you a lot of tools which you can use. And it's not monolithic that you have to use the complete compiler or the complete, you have to use the complete compiler. You can take parts of it and then you can use it as you want. You can even add your own code to it. So that's the power of LLVM project, which is enabling so many technologies, so many known technologies. The picture that you see on the RHS, it might be a little overwhelming for someone unknown. But what I wanted to show is that there are three boxes here: front end, middle end, and back end. A compiler, in the first session, we had just understood that compiler is something which converts your high-level language into low-level language. But it does a lot more than that. So we can divide it into, from a very high level, we can divide it into three phases: front end, middle end, and back end. And since there are different skills required in each of these phases, so dividing the compiler into three such phases has, enabled better code generation in general. So I'll stop here for a moment, and maybe we can, I'll pause actually and let others speak. And if you have any questions, please ask. Did you get a basic idea?
Yes, sure, Brandon. I think adding to that, if you look at other compilers that existed before LLVM, like GCC, they were mostly monolithic compilers. So if you want to include a feature of GCC, you have to include the whole compiler, which comes with a lot of baggage. But what LLVM did, and what LLVM achieved by design was a common intermediate representation called LLVM IR, and a lot of tools built around it to enable you to build a compiler.
I think we can move to the next slide now.
Yeah, I guess.
So this is basically Prerna, you can go ahead. I think
yeah, I think this is what I was talking about in the previous slide, that we can view a compiler as as divided into these three phases, and a lot of things happen in these three phases. For example, front end, you have parsers, lexers, and whatever what we had studied in our college. An optimizer is like, you'll have all those interesting stuff happening, which will reduce your code size. The backend will do the task of, let's say, mapping, generating machine relevant code. So basically something like mapping of virtual registers into hardware registers. Maybe I'll pause and then let Ashutosh continue.
Yeah, Pradeep, do we still have that slide? The next slide. Yeah. So first of all, let's just basically go through a little bit about how actually a program is broken down, right? Like, there's a lot of steps here, and there's a lot going on. So basically, it's the basic question we're trying to ask here is, what happens when you execute a Hello World program, or what happens when you execute any program, really? So what does LLVM do that is different from different compilers, and what do compilers do in general? So this is something that's commonly taught in college courses. So you might have gone through this, but still we'll attempt to map it to LLVM a little bit. So first you have lexical analysis. So let's say your programming language has keywords like if, for, or while, include. All such words are there, and then you have your constants, you have your data structures, you have different things. So all of these keywords are there that need to be grouped. You need to pick up your parentheses. You need to recognize each character for what it is, right? So you first do that in your lexical analysis phase. Your compiler might annotate a left parenthesis as L parens. It might recognize an addition operator. It might recognize a subtraction operator. It might recognize a variable. It might recognize a function declaration. Then you come to your syntax analysis. So here you check for your grammar and you generate a syntax tree. So this, again, in your lexical analysis phase, you only checked for valid tokens. You have not really checked if those tokens are in any legible order, or do they actually make any sense, right? So then you have your syntax analysis phase where you construct a tree. And finally, in your semantic analysis phase, all these three parts together form the front end of your compiler. So just like in your websites, we have a front end and a back end. In compilers too, we have a front end and a back end. But here, the front end is basically what refers to the machine independent part. Like, let's say your C++ implementation, whether you write C++ code on an Intel machine or an ARM machine or on a Raspberry Pi or a mobile phone, you write C++ code the same way. You don't care about the details of your underlying hardware there, right? So the front end is the machine agnostic part of the compiler, which does not really depend on the target architecture or the target hardware. So after the semantic analysis, where you do stuff like type checking and all that, that's where the real magic of LLVM begins. So LLVM has a lot of different front ends. It's not just one front end, right? So let's say you have C++ and C. So for that, Clang and Clang++ are different front ends. Swift has its own front end. Objective-C has its own front end. Julia has its own front end. All of these programming languages have different keywords and they have different syntax, and they have different ways in which they deal with types. So all of them have different front ends. But where the commonality takes over is from the code generation part. So basically, the problem that LLVM is trying to solve is that you have multiple platforms, as Prerna showed in a previous slide. You have platforms like ARM, you have platforms like x86, you have MIPS, you have Spark, you have RISC-V, and you have multiple front ends. So how do you make this job easy? Like, let's say I just want my programming language to run on certain hardware. I don't necessarily need to have to be a hardware expert to just be able to do that, right? So this is where LLVM IR comes in. It's like a portable high-level assembly language that is common across all your different front ends. So there is only one LLVM IR. And although the IR generated by different languages can be different, but you can apply standardized transformations on them. And that's where the magic of optimizations comes in. So this is what compilers do that you don't see every day. They make your code go faster. Stuff like removing constants from loops, or removing dead code, or fusing loops, or vectorization. They do a lot of stuff to make your programs go faster without changing what the programs mean, right? So this is how LLVM compiles code. So this is important because, again, we studied about OPT, and I mean, you hear about the LLVM optimizer, the LLVM front end, and the LLVM backend all being used differently. So let's go to the next slide. So yeah. I'll continue. I think I have to. Yeah.
Oh yeah, just so, like I think I.
Yeah. Sure. You have to cover this.
Oh yeah. So like Ashutosh mentioned that there are various phases in compilation, and this is a more specific example where we have a C++ file and we want to compile that to machine code. And as Ashutosh mentioned, there is a front end, there is a back end, and here there's also a middle end. That it's not much covered in the compiler literature in normal compiler courses, but there is an independent middle end phase as well. So as Ashutosh mentioned, there's a Clang. Here we use a C++ compiler, Clang, and Clang builds what's called an ASC. It's almost a tree-like data structure used to represent your program, your programming language grammar, like LL grammar representations. And Clang runs its parser and builds its ASC tree. And it does a lot of syntax checking in the semantic analysis phase. It also does some sort of code checking. It checks whether you have, for example, given a malloc, whether you have a free, those sort of analysis. And the advantage of using a Clang-based compiler is that you can use a Clang front end as its own software, and not include the other bits of LLVM that you need. So let's say you want to just parse your code and do some sort of static analysis of your code. You just need to include Clang as a plugin, and then start using its API to do the analysis and get your results. So that's the main advantage of using the LLVM compiler infrastructure and the tools that come under. And of course, we'll cover Clang and the tools that are there that we can use to optimize the developer workflow. That's coming in the future. And once we generate the AST, we generate the LLVM IR code, which is done by walking the AST. And LLVM has its own API that allows you to build the LLVM IR in memory, or you can dump it to file and whatnot. And once you reach LLVM IR, so the main pinnacle of LLVM is the LLVM IR representation, which is the centralized representation that various tools in LLVM can use to make their own transformations. For example, the LLVM library comes with a lot of transformation passes. I wouldn't call them optimizations because a transformation can be beneficial for one scenario versus another scenario. For example, if you want to do inlining can be beneficial in a lot more cases, but there are cases where you don't want to increase your code size. And so that there are memory requirements for a specific kind of hardware, that inlining might be a more of a de-optimize or a bad optimization that you want to apply. So it's better to call it as a transformations, and LLVM comes with a lot of transformation passes that take an IR, mutate them, and generate LLVM IR. So this is what cool about it, is that you keep on using the LLVM IR representation. And this allows you to write more maintainable code, where you can write test cases that transform code, and you can verify that this transformation is legal or not by writing unit tests for that matter. And LLVM has a very well maintained unit test software called LET, and a lot of unit tests in LLVM are written through it. And once you're done with a lot of optimizations that's happening in the LLVM IR phase, you start to lower your code down to machine level. So whatever you did in LLVM as target independent optimizations, and you start to lower that to a machine friendly representation. Here there's selection DAG. There is also a recent project called Global ISIL, which is even more better representation. Now, for the sake of simplicity, we'll stick to selection DAG, which is a DAG-based representation for representing instructions. And once you have a selection DAG, you then lower to machine IR. So machine IR is not a machine code, but it's more of even higher level abstraction to the machine code. For example, let's take x86, you have registers. The machine IR still has a concept of a virtual register, which is not actual register that's used in the hardware. And you also do some sort of machine-specific optimizations here. For example, you do dead code elimination, global value numbering. You also do loop unrolling, loop invariant code motion. But here you also factor in the properties of the hardware. Right. So those are the machine-specific optimizations are done in machine IR, and once you're done with them, you start to do register allocation and then scheduling. Register allocation is when you convert all these virtual registers that are there in the machine IR to actual physical registers, and then you generate the machine code.
Yeah, so I just wanted to add briefly that it's not the topic of the presentation, but all these stages that Pradeep has shown here, it's not like your program goes from point A to point B directly. It actually goes through all these steps, and with the right set of compiler flags, you can actually see what the Clang AST looks like. Or if you have semit LLVM as a flag, you can actually look at what the LLVM IR looks like. You can see the result of various passes through the OPT viewer. So basically, you can write your own simple programs and break down the program piece by piece and invoke, say you can invoke the preprocessor separately, you can invoke the optimizer separately, and you can call the assembler separately. So all of these are things that are actually happening, but it's just that when you call Clang, the Clang driver, it executes all of those steps at once. And all of that complexity is hidden from you. But if you want, you can see each step happening in person. Yeah, that's it.
Yeah,
I
thanks,
also
Ashutosh.
wanted to add one point. So, I mean, whatever Pradeep and Ashutosh are explaining, there's one point which is which you will see, there are so many representations of your input program. You have Clang, ASTF, LLVM IR, selection DAG, so many representations. And sometime back we saw that the compiler also can be divided into multiple phases. So when we divide a compiler into multiple phases, the front end, middle end, and back end, we facilitate better code generation, better scope for better optimizations. Similarly, whenever we are having multiple IR representations, multiple representations of your input program, we enable better optimizations for your input program. And that was the point which I wanted to highlight. So it's logical that we have so many representations of your input program. And the more we go closer to the hardware, your IR becomes more similar to the assembly language. So yeah, I wanted to add that point.
Yeah, sure. I think there are a few questions in the chat. I think one is that, can you please provide an example after each stage? I guess this is not the topic of the presentation itself. I think Ashutosh has shared a link to the previous presentation that he gave. But we will go through some of the stages in the future talks where we cover some of the individual tools that are there and how they use each representation in the LLVM IR pipeline to do analysis, transformations, and everything like that.
We have a question, Pradeep. Is the intermediate representation something like a virtual architecture that can be mapped to any one of the different physical target architectures?
Yeah, exactly. Yeah, I think it's still a virtual architecture. I think LLVM, when it started, it was called low-level virtual machine, and because it's the assembly itself was a virtual architecture, a RISC-like architecture, where you have loads and stores and operations in memory. And so it's a very low level, but it's not assembly. So that's the main difference here.
Yeah, we can move to the next one.
There's another question. Does this modularity introduce any performance cost? I'm not sure what you mean by performance cost here. Do you mean the performance of the generated code versus or the performance of the compilation itself, compile time taken? What do you mean? What do you mean by that?
In any case, GCC and Clang are two examples you have of compilers for the same language, right? And they're very neck to neck in performance. So I think there's not any obvious disadvantage due to the modularity itself, because we have different in compilation time. Okay.
Okay.
So yeah.
Yeah, I think there's a trade-off there with compilation time. So the more optimizations you do, there are code transformations that happen that takes time. And there is also a trend, trend in LLVM that the compilation time of LLVM keeps increasing as the releases come out. I think there is a hit on compilation time when you do a more aggressive set of optimizations in the compiler pipeline. But that said,
most folks are usually happy to take a small hit in compilation time if it means better quality code generation, because typically, unless you're working in a use case where you have to compile something again and again, the quality of the code generated for your binary and how fast the binary is sort of a little bit more important than the compilation time. There are efforts to track compilation time across LLVM, but again, it depends on, as Pradeep said, it depends on what you do with the code. Like if you build something at a high optimization level with like O3 and FLTO and other such flags, it is going to take longer to compile, and the code size will be a lot more at the expense of speed. So yeah.
Yeah, I think so it mentioned LTO, which is a link term optimization, where you have a large set of individual CPP files and you compile them to object code, and before doing any optimizations, you combine them into a single monolithic IR to compile and to run optimization. So that also takes a lot more time to compile than a regular compilation path. So that being said, I think to add to that, there are cases where compilation time is very important. For example, interactive applications like Photoshop or a game, for example, where you need interactive use interactive time. So let's say you want to generate a picture, or if you want to do an edit in Photoshop, your compiler has to do all these, take a shader and then compile and then generate the respective output. It should be interactive fast enough that you don't see your application hang and then wait for it. So there are cases where compilation time is important, but in most cases you would see performance as a main criteria. And I guess there are cases where you also want to reduce the level of optimizations. For example, there are limitation on code size. For example, phones have a requirement on code size because the more code that you have on your application, that comes with power and energy costs. So yeah, I mean there are a lot of trade-off in the compilation pipeline. So that's what I said. These are transformations that you can add based on your use case. These you don't call it as optimizations, you call it as transformations, and each transformation has its own use case based on the target application. So
let's continue because we have a lot to cover.
Oh yeah, I think we'll also take the questions to the end. I think there are some interesting questions. Yeah, I think we'll take the questions towards the end. Yeah.
Sure.
So moving on, so now we'll go through some of the examples where LLVM is used in the wild. I think yeah. So please take it away.
Yeah, so Apple gets its own slide because Apple's sort of really closely involved with the early history of LLVM. One of the reasons that Clang, the C and C++ frontend for LLVM was created was because Apple wanted a default compiler for Mac OS that was not GCC to licensing reasons. So the Xcode is the default IDE in Mac OS, and it uses Clang as the frontend and LLVM as the code generator and LLDB as the debugger. So basically, if you used Xcode, you used technology built on top of LLVM. And the Swift programming language itself is one of the front ends for LLVM. And Swift is used for iOS app development and several other Apple-centric use cases. And Swift's predecessor, which was Objective-C, was also one of the front ends for LLVM. So this is one example. And Pradeep will take you through SPIRV and OpenCL, right?
Right. Yeah, thanks, Ashutosh. So one of the the outcome of LLVM project was the OpenCL compiler, OpenCL programming language, and the compiler and the runtime. So LLVM has been used to create a broad number of products, and one of the important one is the OpenCL GPU programming language and runtime. And OpenCL, as you guys know, is a parallel programming language for compute shaders / kernels. So this is similar to in a more popular term, we have there's CUDA, which is a proprietary GPU programming language from NVIDIA. OpenCL was started as an open source an effort by the Kronos Group, led by a lot of companies, including Apple, Google, including NVIDIA, AMD. And OpenCL, the main advantage of using OpenCL is that you can take an OpenCL program and run it across different platforms, whereas CUDA is restricted to NVIDIA. And the OpenCL language was also built around LLVM compiler toolchain, and one of the common compiler frontend used is the Clang frontend. There are various OpenCL implementations that use Clang as a frontend to compile to what's called the SPIRV. We'll talk about SPIRV later. But that said, yes, SPIR is a intermediate representation. SPIR was inspired by LLVM. The main reason being that LLVM IR was mostly designed with the CPU in mind. So LLVM started around 2000, and there was no concept of a programmable GPU at the time, and so most compilers were CPUs. And LLVM IR the IR itself is designed around CPU in mind. And when GPUs came about, there are a lot of constructs that LLVM missed that's required for optimal GPU compilation. And Spear was the integrated representation that derived from LLVM to support those cases. And so I think I'll give you an overview of the whole Spear OpenCL ecosystem. So this is a whole suite of compilers and representations that that the Chronos group defines. There is OpenCL for compute language, and there is a SYCL, which is a more C++, modern C++ implementation that's also based on all these tools revolve around Spear as the interpreted representation, which is also based on LLVM. And then you generate different backends based on it. For example, Vulkan, HLSL for DirectX, and there is also different kinds of projects that run OpenCL on DirectX and whatnot. So the point here being that the LLVM and Clang, all these subprojects are very important in the GPU ecosystem. So if you want to work on GPU compiler, then I think LLVM is also a necessity that you should know. So that being said, let us talk about Android, LLVM on Android.
Yeah, so one of the very interesting places where LLVM's taken over is the Android NDK. So you might know, if you've ever developed Android apps, that Android has an SDK, which is the standard development kit, which uses Java and now Kotlin, I believe. But the NDK allows you to use C and C++ code with Android. So previously, NDK used to use GCC as a compiler. And this had a problem because GCC is monolithic and it does not have a modular design. For each target architecture like ARM, AR64, x86, you had to have a separate copy of GCC built with that individual target configured. So this led to like a lot of duplicate binaries and a lot of increased binary size, which is sort of important in mobile devices, right? So Clang and LLVM, on the other hand, it can handle any target, any architecture that is with one single compiler executable. So with Clang, we save a lot of disk space. We avoid having a lot of different executables. So till our revision 17, LLVM and GCC both were shipped with Android NDK, but since R18 and currently we are on revision 25, so this change happened back in 2018. LLVM is the default compiler in Android NDK. Its GCC support has been completely removed. So we can go to the next slide for. Yeah, so here's one very, very interesting use case of LLVM. LLVM is used for hardware design tools. So as you know, you might know that hardware companies, semiconductor companies, they all use hardware description languages, HDLs like your Verilog and VHDL, and they have specialized software known as EDA tools used for developing chips. So basically, if you have to create the next Intel or NVIDIA or AMD processor, you need specialized software to work with those chips and to validate those chips and to create those chips. So the problem in this space was that basically there were a lot of different EDA tools from Cadence Systems, from Xilinx, from such as Vivado and Vitis and many others. So CIRCT, which stands for Circuit IR Compilers and Tools, it's an attempt to apply LLVM and MLIR methodology into the design of EDA tools. So this is actually a very new project. I'm not sure if any commercial software uses CIRCT yet, but the attempt is that the way that LLVM sort of unified different architectures under one common LLVM IR, we'll be able to use CIRCT to do the same. So how it does this is basically the RTL code, which is the low-level hardware description code. In hardware design, it's like an IR. It's like an intermediate representation. So we can use software compiler technology to translate the IR level of the RTL. So it's a very interesting project, and it's currently under very active development. And it has its own website, circt.llvm.org. So you can definitely check that out. So yeah, next slide, please. So another very interesting use case is computational photography and image processing. So a lot of us have used Adobe tools such as Photoshop, InDesign, Illustrator, After Effects, and a lot of us have mobile phones that run Snapdragon chips. So over here also LLVM makes an appearance. So Halide is a DSL. Now, what is a DSL? A DSL is a domain-specific language. A domain-specific language can be basically thought of as software designed for one particular use case. So like you can take an example of SQL. We have all used SQL, and SQL is very good for databases, and it's really designed for that one purpose. So similarly, Halide is a language that is really designed for computational photography and image processing. Basically, what the author surmised is that traditional languages that make use of expressions of parallelism, tiling, and other optimizations, it's very difficult to describe all these things in traditional languages. So you can see that sometimes OpenCV code can be horribly convoluted to write. So Halide enables rapid authoring and evaluation of optimized pipelines by separating the algorithm from the computational pipeline. So LLVM is used in two places here. One is the LLVM stack is Clang is used for the front end, since Halide is described using C++, and it's used for compiler target, since x86, ARM, Hexagon, and many other backends are supported by LLVM. It's used to basically power this technology that enables you to write very fast code for image processing and computational photography. So your phones have various effects and modes like bokeh and various filters. So that's where Halide comes in, and it can do stuff like image sharpening and a lot of other things. So next slide.
Hey, there are a couple of questions in the chat.
Sure.
So ARM, ARC64, x86, as you said, they are target machines. Then as for device perspective, only one binary works on that particular machine. How will it create duplicate GCC, or am I missing something?
So basically, let's say you have one common front end, right? So let's say you have a common front end and you generate an executable with LLVM IR. So now that LLVM IR executable can be executed on any hardware platform. And for GCC, there's no way to really create a platform independent executable. While with the LLVM, it is. So that's how that works.
Okay, there's another question. HTL come under domain-specific languages, and as far as I understand, MLIR was used to do unite and simplify compilation of HTL, right?
So that is correct. HDL does come under domain-specific languages, and MLIR is the main project used in CIRCT. But MLIR is also a part of the LLVM project. So by LLVM over here in the beginning, as Prerna said, we refer to the LLVM project. And the LLVM project GitHub repository, it includes MLIR and all other sub-projects such as LLDB. So the main technology that powers CIRCT is MLIR. That you're right about that. Yeah.
Okay, moving on.
Yeah. So one more way, unique way of using LLVM is in databases, more specifically in Postgres. So Postgres is a very popular relational DBMS that many of us have used in college and many of us use at work. So basically, Postgres now has built-in support to perform JIT compilation. So the way SQL queries are normally interpreted is by using an interpreter. Line by line, you interpret the SQL query. And while this works well enough for like very short queries, if you have very long or very complex SQL queries, especially if something where parallelism is possible, then you lose out on a lot of performance just because you're using an interpreter. So JIT compiling is basically a process of turning some form of interpreted program evaluation into a native program and doing it at runtime. So for example, instead of using a general purpose code that can evaluate like SQL expressions, we can have a function that is specific to that expression and can be executed by that CPU. So Postgres has been using this for a few years now, and they have gotten a speed of about 5 to 6 times for the execution of some of their SQL queries. So it uses LLVM as a JIT compiler, and now I believe it comes built in with the thing, but yeah, you can explicitly build it with LLVM. So next slide, please.
Yeah, thanks, Asos.
Yeah.
So, here we talk about IRE. So IRE is an intermediate representation execution environment. It's a more of an end-to-end compiler for ML models. So let's say you have various front ends like Pytorch, JAX, or TensorFlow, or TOSA. What you do is you compile that to a graph-like representation and you feed it to IRE. And IRE, based on the requirements, whether you want to run it on a CPU, GPU, distributed systems, what it allows is that it provides a unified representation of an IR and allows you to execute on a wide range of platforms. And the representation that IRE uses is based on MLIR, which was released around 2019, and MLIR is a very huge project. I think it deserves the talks on its own. But yeah, I think it borrows a lot from the LLVM subproject, the LLVM project on the design of it. It's modular. It's the pass pipeline looks similar. It's more modern, and it's also multi-threaded in the sense it's passes compiled using multiple threads. I think IRE is more of a package where you provide a ML model and you can run it across various devices. And as you can see in a much bigger image, that you can see IRE modules, and what you can do is you can have a virtual environment where you can also compile that to CPU, CUDA on any platform that's in existence. And moving on, so this comes to the last slide of the talk. So what we had is this as tip of the iceberg of all the projects that use LLVM. I think we'll talk to some of the projects. Let me start with Azel. I think some of them mentioned Java bytecode. So Azel is a Java tier 2 compiler that uses LLVM as an optimizer for this JIT compiler. And also, you also know about C++ Clang compiler. Clang is one of the famous compiler that's default in Apple, and it has a lot more advantages that we'll talk about in the coming series of talks. So CLAD is an interesting tool. Is that it's a plugin that's based on Clang that does automatic differentiation. So given a C++ code, what you can do is you can run CLAD on it, and what I'll look through all the functions and do automatic differentiation on the code and generate C++ C++ functions that you want to differentiate. And Halide is an interesting project that that verifies compilation of LLVM passes and make sure it generates valid code and does not have any unexpected side effects. As Stuart mentioned, that is a Julia project. Julia is built on top of LLVM, and the advantage is that it allows Julia to target a lot more different backends that LLVM comes with. And I also want to talk about Unity. Unity has a compiler called Burst, which compiles .NET bytecode to x86, and it has its own tune pass pipeline to be used in game engine environment. So if you're using Unity, you're already using LLVM. So one of the early users of LLVM is NVIDIA CUDA. So NVIDIA has an open IR specification called NVVM, which is based on LLVM IR with extensions, and it's used to represent CUDA specific optimizations for GPU code generation. I guess Ashutosh and Pranav, do you want to talk to some of the tools here?
Yeah, so LLVMs, yeah, please go ahead.
Okay, I just wanted to add one thing. So the NVVM IR is converted into PTX. So for that, they are using the LLVM compiler. They are basically extending on the LLVM compiler to convert from your NVVM IR to PTX. That's what I wanted to share. And we can probably ask a question to the audience here. So if you have been attentive throughout our session, then which part, like how is the LLVM infrastructure getting used here? Is it being used as a front end, middle end, or a back end? So maybe you could answer that in the comments. Thanks.
Yeah, so one more interesting place was in the machine learning ecosystem. One of the ways where, like especially where the MLIR project is taking off, MLIR is a thing that deserves a talk of its own, but it stands for many things such as multi-level IR and machine learning IR in some cases. So you have very exciting projects like the Mojo language that Chris Latner has unveiled recently that has several hundreds of times more performance than equivalent Python code in some cases. And TensorFlow and Pytorch also make use of LLVM. So there is really this interesting space of using machine learning in compilers and using compiler-based technologies in machine learning. It's a very hot topic, and there's a lot of research being done in this area. So
yeah, thanks, Ashutosh.
Yeah,
I think as you mentioned, it's just a tip of an iceberg. There are a lot more projects that use LLVM that we cannot list down here. You can go and check out. I don't know if there is a centralized repository for that, but yeah, if you come across any tool, yeah, just ping us in the WhatsApp chat. So good for people to know.
I think next slide is for questions, right? We can open to questions.
Yeah, I think this is a usual slide that we put out that these are a list of links that that you can use to stay on top of the LLVM up to date on LLVM. So there's LLVM Weekly, which is a weekly newsletter that Alex Bradbury publishes, on the recent happenings in LLVM on the previous week. It has a lot of interesting links on blogs that came about, the comments on each of the sub projects that you found interesting. I would recommend, if you want to stay on top of LLVM, LLVM Weekly is the best place to start. There's LLVM Discord server where folks from the community, people who actually work on LLVM on a day-to-day basis and who maintain the sub-projects in LLVM are present there. You can ask questions ranging from a beginner level to an advanced level question, and there are folks there to answer those. And there are channels that are specific to each of these projects, and we also have an India specific channel where you can just join and ask questions. The LLVM Discord page is a forum where you can also ask questions, but it's more of a more formal forum where you can post a really long question and and ask for there are other people who post RFCs on new features. You can also find job listings as well, and I think this is the official forum for LLVM. where there are community announcements on the recent conference talks, etc. Of course, there is the LLVM YouTube page where you can find recordings to all the LLVM developer talks. There are actually two main conference talks. There is the LLVM developer meeting that happens in the US, and there is a Euro LLVM talk that happens every year. And you can find a lot of interesting talks that are catered for beginners as well as advanced users. So LLVM Office Hours is it's another initiative by the LLVM Foundation to help people get started on if you have any doubts, you can there are people who block their calendar on a specific time of the month, and they are available for a one-on-one interaction where you can talk with them directly on questions that you have, and each people will have their own set of specialities, fields that are interested in, and you can also post general questions, but you can go to the page and look for folks and the related topics that they're handling, and you can join their it's usually a Gmeet chat. You can join in and ask questions. And yeah, there are project specific meetings. There are there are sync ups for RISC-V, MLIR, Flang, various others for projects. They have weekly sync up meetings where they present on what they're working on and upcoming tasks. You can just join them. It's more of a meeting for developers, but you can just join in to see what they're working on and how things are done in LLVM. And of course, there is our LLVM Social Bangalore meetup page, our YouTube page, where you can go and watch our talks from the past meetups. And with that said, that brings down to questions. Thank you for joining in and staying till the end. If you have any questions,
And Pradeep will be sharing a link to our WhatsApp group that we've set up, because this is a part of a lecture series. So there are a lot more talks, in fact, 8 more talks that are planned in this series covering various tools and technologies. So he'll be sharing the link in the chat. In case this is your first meeting, please join us so that you can stay updated about the upcoming meetings, and you can ask further questions and try it out. So yeah, we'll be taking questions. I think a few folks raised their hand. Please go ahead and unmute yourself and you can ask.
Hello.
Yeah.
Am I audible?
Yeah.
Well, yes, I'm new to LLVM and I joined the first meeting. So I was thinking there was a mentorship program type thing that was submitted. So I was thinking if there is any kind of update on that, and I was thinking about getting some guidelines on contributing to the LLVM project if there is anything available.
Okay, I think I think we mentioned the ACM SIG plan mentoring thing, right? So that is sort of an independent thing that you have to apply to. And other than that, you have to really elaborate on what you mean by mentorship, because what any mentor will really do is they can provide you a link to resources. They can tell you how to get started. So if you can basically tell us a little bit more about what you're looking for, then we could probably help you out.
I was looking to contribute in the LLVM backend in optimizations and kind of GIT stuff. So I was looking for the mentorship, and I was looking how to contribute in that. The LLVM structure is too big, and I was thinking where to start and how to get the resources too big. So it was a bit overwhelming for me. So if there was any kind of solution for that.
I think
I believe last.
Yeah, go ahead.
Yeah, sorry, Brian.
Oh, I believe last time we had similar kind of questions, and there were a lot of links which were posted on the chat. So maybe we were planning to actually make a compilation of all of it and share with all of you. Maybe so. Pradeep and Ashutosh, this is the right time, right, to kind of
yeah, we'll do that.
have all
And yeah, and other than that, it's sort of important to start exploring on your own. Like, I think the best thing to do would be to like start writing your own small programs and breaking them down using compiler flags. Then trying to build LLVM. There are guides on the LLVM website on how to write a pass and how to write a toy language using LLVM. It's called Kaleidoscope. So there are some beginner pages like that. We can give you the links to those. Okay.
Thank you.
Yeah. Okay. Sure. Any other questions? Okay. There's a question in the chat. When new hardware is launched, do companies contribute to LLVM for the optimization for machine IR? So this is a very good question because this is basically the crux of the job that most of us do. So basic support has to be added by the company. So I'll give you an example of my own company. This year, AMD released its Zen 4 processors. So the basic support for ZNver for Zen 4 was added by our own team, but it also depends on how much they are willing to upstream. Typically, all companies want that basic compilers should be able to run on their platform. So yes, basic support will be added, but a lot of these companies such as AMD, NVIDIA, Intel, they also have their own platform-specific compilers that are based on LLVM and are more optimized than LLVM for their own hardware platform. And the upstreaming policies differ. Some companies are very liberal with what they upstream. Some are not so liberal with what they upstream. But yes, companies, a large majority of LLVM's contributors are paid contributors who are working in companies, various semiconductor companies and other companies like Google and Microsoft and other some such. Okay, we have two folks who raised their hand, I think.
Yeah, so adding to that, so there are a reason why the people don't contribute to LLVM IR for reasons of IP protection, because some of the implementations are based on their hardware, and they don't want to leak some of their hardware IP just because they want to upstream people. Yeah, that's some of the reasons why people don't upstream things.
Yeah, that's right. Especially in the back end, the optimizations can reveal secrets about how your company's hardware works. And if you don't want that out in the open, you're probably better off not open sourcing that. Any other questions? I think one person has raised their hand.
Subtrative Jenna, can you please unmute yourself and ask the questions?
Hi, am I audible?
Yeah, go ahead.
So particularly this community, right? Do you guys also have any physical meetups ever?
Yes, we do. Actually, we do usually meet up once a month or thereabouts, but our physical meetups are more targeted towards advanced topics for or people who are already compiler practitioners, although anyone is open to attend them. So we'll publish details about that on our meetup page when and where those meetups happen. It'll be somewhere in Bangalore, and you can follow the meetup page for details on that. But this series is online. Yeah.